Hi. So today, our topic is about pulmonary circulations. As you see that, I've already pre-drawn some of the graphs, so that some of the pictures actually. Sorry, graph I said. So that way, actually, so we can actually move a lot more faster. Whenever we talk about pulmonary circulations, we need to also mention about systemic circulation, because there are two circulations in our human body that we often talk about. One is pulmonary circulation and the other one is systemic circulations. So we have to know what are pulmonary circulations, and we also have to know what are systemic circulations, okay? And we have to compare, and we also have to discuss about what are the similarities between pulmonary and systemic circulations and what are differences, and we have to mention about that too, right? But before I go about the pulmonary circulation, distinguish between two different things, let's start with what are the functions of your pulmonary systems. Let's talk about that first, okay? So one of the functions of your pulmonary systems is, okay, like if I have to write down here, okay, let me just write down on top here. So one of the functions of the pulmonary system is that everybody knows that it exchange, you are going to exhale CO2 and then you're bringing oxygen in, okay? So the exchange of your gases, that is what one of the main functions of the respiratory system, right? That everybody knows. Now, other function that we have to talk about the respiratory systems. One of the functions of the respiratory system is what? It also acts as a defense mechanisms, okay? And I'm writing it down, and we'll talk about what does that mean, okay? What else? Respiratory systems also plays a role into for the immune systems. It also contributes in it has some immune function too. Okay, we have to talk about that. Respiratory system has some metabolic functions, and we also have to mention about what does that mean. Okay, and then obviously there are other functions okay, let me write it down here. The metabolic function, defense mechanism, immune systems. What are the other functions? Okay, obviously phonation, that we have to talk about the phonation too. Okay. One of the things is that one of the functions of I'm just mentioning this, but then we'll talk about what each one of them also means. One of the other function is it acts as a filtration, okay? And we'll talk about what filtration that means. There's other ones, some of the functions, not only it acts as a filtration, it also acts as a what? Acid, acid-base balance, okay? It also does that. And we'll talk about what that means. We'll mention about a couple of things. 8, what else it does? There is also, look, this one, along your pulmonary system, it also acts as a reservoir for the left ventricle, actually, a left heart, we'll say. And we'll talk about what does that mean, okay? Number 1, what else? Is there more function? There are other functions as well, but these are some of the functions that we also there are synthesis for some of the enzymes too. Let's just say synthesis of some very, very important the chemicals, we'll say. Okay, now these are some of the functions of some of the functions of respiratory systems that I want to list. Okay, so let's just go each by each. What does that mean? Okay, so everybody knows that respiratory systems plays a very important role for for your gases exchanges, right? And maybe you also know that it plays as a defense mechanisms, which basically means is that, okay, whenever you have anything let's say any irritants comes in your systems, so what happens is that it irritates your bronchi, or then what it does is it creates cough reflexes, okay, and they are able to throw out those whatever mucus or whatever noxious substances, okay. It create a cough reflexes, or Also, like, your nasal area, if there are like any sort of bacterial pathogens that are like greater than like 10 to like 15 micrometers, what happens is like they will, because of the hairy, those nasals of the hairy cells, it will get trapped into it, right? And they will act as like front defense mechanisms to actually prevent anything to get in. Okay, and we've already talked about that kind of other stuff too, in other places too. They play as immune function, meaning like alveoli, alveolar, they have so-called like the alveolar macrophages. Okay, and what they do is like they'll clean up any sort of like dust particles, so that way, or they'll clean pathogens, or they'll eat any sort of like microns that gets anything that's less than like 2 microns. If they get into alveoli, they will clean it up. Okay, they have the metabolic function. What are those metabolic functions I'm mentioning about? Remember, like, guys, if you guys remember that, let's say this is I made this as a pulmonary like arteries, right? Right here, what happens is that in the pulmonary arteries, pulmonary capillaries and arterioles, those cells are lined by what? Those cells are lined by important types of cells, and these cells are, let me just write down here. These cells are endothelial cells. Okay, they're continuous endothelial cells, and what happens is that they're like in the pulmonary capillaries. Okay, we see the pulmonary capillary beds. There is endothelial cells, and these endothelial cells have important enzyme called ACE enzyme. So which basically angiotensinogen converting enzymes. Remember, what happens is that it plucks out like extra 2 amino acid from the angiotensinogen number 1 and makes it angiotensinogen number 2. And this angiotensinogen number 2 is very, very important. Remember, this angiotensin does a lot of function because this helps with like raising your blood pressure, right? So this is one of the functions of like the metabolic functions of your enzyme. This is very, very important. I really want you guys to remember this, okay? And other thing is that these endothelial cells are also very, very important for secreting like or making like nitric oxide too. And remember what nitric oxide does. Nitric oxide is very, very important, right? What it does is it's for the vasodilations, okay? It is for the vasodilation. It helps with increasing the downtown diameters of this capillary, so which helps with the resistance. So if you have whenever you increase the diameter of something, what happens to resistance? Because if you remember, resistance is equal to what? 1 over the radius 4, right? 1 over the r. So basically, let's just say if my r is increased, the radius, then what happens to my resistance? It will go down, right? So you'll have a good blood flow. So that's what also it does. There's also other things that I have to mention is that, like, a lot of times what happens is, most of the times, from the mixed venous blood, what happens is a lot of these chemical agents like serotonin or other like prostaglandins or histamine, all of them are actually could be like or especially norepinephrine. This could from there it could go to the lungs area, right? But what happens is that the pulmonary endothelials are very for known to like extracting this serotonin especially and removing the 90% serotonin. Okay, so you can say this like they also produce like great amount of serotonin in endothelial cells. What else? They also have like produces heparin molecule. Remember, heparin is what? Heparin is for anticoagulant, right? So a lung has like greater amount of heparin for like actually fighting heparin for like actually for the anticoagulant, so it doesn't allow any blood clot to form there. They do very important things. All right. There is that's something that I wanted to mention. Okay, they do produce like a lot of prostaglandins to actually to protect those epithelial lining of those endothelial linings of this of the cells. The cells of the lung can produce that. Okay, now. And other one is like I said about phonation. Now, what does a phonation means? Basically, if you guys know, like, okay, this one is, what is this? Right here, this is going to be my trachea, right? On trachea, what happened? On top of this, let's just make this is my pharynx right here, right? Sorry, this is my thyroid cartilage. And what happens with the Adam's apple, like down here, there is what do you call these vocal cords, right? These vocal cords, whenever these vocal cords come together, what happens? Whenever the vocal cords come together, when they adduct, right, what happens? The air, whenever air try to go through, like from the air, when they try to go through, what happens is that And then when these vocal cords come together, when air passes through this path, this vocal cords vibrates. And when the vocal cords vibrate, that produces sound, okay? So it's very important. The respiratory system are known for the phonation, right? What is filtration? Filtration basically means, like, guys, sometimes what happens is, like, you know, a lot of this like blood clot, like emboli, let's say, like from here, like, let's make this as from here, like small, from the here, like emboli, or let's say like thrombi, okay? They can actually go from the from your blood circulation from the venous, and you go to, this is my, I'm just going to name right down here, this is going to be my right atrium here, and let's make this a right ventricle, okay? And this is going to be like, okay, the venial side, and this is going to be like, let's make this as the mixed venous blood, which is a inferior vena cava, which is carrying this blood. This is going to be my right ventricle right here. This is going to be my pulmonary artery right here, okay, because it's carrying mixed venous blood, right? Whenever it comes, what happens is that whenever it comes to this, guys, these pulmonary capillaries, they are very, very thin, right? They're very, very thin and small. And what happens is that whenever thrombi comes in, this thrombi can get kind of lost into these pulmonary capillaries. And whenever, let's say, they're lost into it, what happens is endothelial cells can actually release some kind of like a fibrinolytic, like fibrolysis sort of like activator, okay? Fibrinolysis activator, we said that. Like fibrinolysis, I mean, check the spelling, guys. Fibrinolysis activator, right? And what it does is that any sort of like fibrinolysis activator, which actually converts your plasminogen into like plasmin. And what plasmins are good for? It can break down this clot. Okay, it can break down the clot. So it really prevents any sort of clot or emboli to actually go to the systemic circulation, because if they go to the systemic circulation right here, like this is going to be my pulmonary vein, okay, because it's carrying oxygen in blood. That's why I do on the red side. And this is going to be my aorta right here, okay, aorta right here, and this is going to be my left atrium right here, and this is my left ventricle, okay, and this is my aorta going back to the systemic circulations, and then these are going to be tissues, okay, and we'll talk about it as we go. So lung plays a very, very important role for the filtrations, okay? It's prevent any sort of like any sort of emboli or thrombi to actually prevents from going to the systemic circulations by releasing this fibrinolysis sort of activator, okay? That's what they do. That's what they work as filtrations. They also work as acid-base balance. What does that mean? Meaning, remember, guys, whenever you have, like, let's say you have a lot of metabolic acidosis, right? Whenever you have a lot of protein concentration is went up, or let's say a lot of carbon dioxide, this arterial carbon dioxide, or on the arterial side, really, what happens whenever they go up? What is going to happen? This is going to cause central chemoreceptor, right? This is going to report to from the circulation, because remember, from the aorta, from here, where this can go? What are my systemic circulations? What are my system circulations? Those are what? Those are I'm going to write down here, okay? It's going to be one is going to be my brain, right? It's supplying to the brain, right? This is system circle. Other one is supplying to what? Kidney, right? Your GI system, correct? Your skeletal muscles, right? Your skin. So it's supplying to all its organs, right? From the aorta, like they're going to. So whenever it goes to the brain, what happens? Whenever the high carbon dioxide level, it's going to stimulate central chemoreceptor, right? Or like this proton, like a high level of this peripheral H+, they can stimulate the peripheral chemoreceptors. If you haven't, you guys need to know about the neuronal circulations. If you know about that, you know that it will stimulate the peripheral receptors. And what happens is that when you stimulate receptor peripheral, what happens? It can cause hyperventilation. So it can puff out more carbon dioxide, right? So and bring it the pH to normal level. Because remember, that's what it does. So that's why the respiratory systems are also very, very important for the acid-base balance. Okay. Other one is like, look, we said that this 8, it works as a reservoir for the left ventricle. Meaning what happens is that, you know, this capillary, like normally what happens is that, this lungs, you know, this capillary, sometimes what happens, they can accommodate some volume of the blood, meaning they can hold the volume of the blood, and they hold about like 600 ml of the blood, right? And what this does for the left ventricle, so let's say when you take inspirations, what happens is that whenever you take the inspirations, what happens is that everything, like thoracic cavity goes down, it pushes on abdomen, so your venous return, everything increases for your right side of the heart, right? Right side of the heart. But, and the cardiac output also increases for the right side of the heart. But at the same time, the left heart cardiac output decreases. The reason why is because even the cardiac output goes up, what happens, those increases, they go and sit in the pulmonary, the pulmonary capillaries, okay? So that's the reason why those extra volume of blood gets stored during the in a pulmonary capillary beds. And usually like during expiration, what happens, those blood volume that is stored in your pulmonary cap, that get pushed out. So during the expiration, what happens is that your left side of the cardiac output increases, but then the right side of the heart or cardiac output decreases. And also other sometimes, like if you have some kind of hemorrhage on here, let's say there's a hemorrhage in this blood vessel right here. Okay, this is a systemic circulation right here. What happens is that sometimes this, in that case, what happens is that this lung can actually release those extra like 600 ml of the blood they are holding and send it to the right left side of the heart. So that way they support this left side of the heart. Left side of the heart to provide extra blood. Okay, so they play a very, very important role. So they act as a reservoir. Okay, now we also said like it acts as synthesis of chemicals, right? Remember, lungs are known for producing like very, very important molecules like surfactant, right? Like surfactant is very, very important because surfactant means surfactants are produced by this alveolar type 2 pneumocytes, and they are for reducing surface tension, right? We talked about that many times, and it helps with our breathing, right? It decreases the work of our breathing, and it makes the lung compliant, right? They also have, so like, you know, if you remember, there are cells like Klopf cells or Clara cells, right, in the respiratory bronchioles, and what happens that these guys are very, very, they have this important like P450 type of enzymes, right? And they are very important for detoxifications, okay? They also play that. And also like some of the endothelial cells also produce like histamine, okay? The smooth muscle cells, the histamine, and these histamines are very, very also important, right? Because what are they, whenever the histamines and the smooth muscle cells, what happens if they get stimulated? What happens? It causes the bronchial constrictions, right? These are very, very important. Now, so these are like some of the functions of your respiratory systems that or pulmonary systems that I had to mention about, right? Now we did that. Now let's go and talk about, okay, so once we talk about this, we have to talk about now we'll talk about this is the whole pulmonary circulations, okay? We'll talk about what is the difference between the pulmonary circulations and systemic circulation, right? So let me just erase this part. And we'll talk about, okay, first thing is, in a way that, first thing we have to know is that we have to know the pressure. The first thing we have to know is that what is the pressures in each one of them we have to go from. Okay, generally what is the pressure in your left atrium? Okay, usually it's like what, 5 to 10 millimeters of mercury, right? That is the thing. And usually what is the pressure in your left ventricle? Anything? Okay, we'll say this pressure is here. What do we say? We can say here, this is from like a 0 to 120 millimeters of mercury. That's the pressure of the left ventricle, right? And what is the pressure in aorta right here? It's a 120 over 80, right? And then what is the pressure on my capillaries here? Is it like, I don't know, 20 or 15 millimeters of mercury? And then when the pressure gets to like inferior vena cava, it becomes like what? Like 6 to like 7 millimeters of mercury, right? And here we'll say that in my right heart, it's about like 2 to 5 millimeters of mercury. Right? And what about this? Right ventricle, the pressure is here from here, like 0 to like 25 millimeters of mercury. Right? And then what is in the pulmonary artery right here? This is my pulmonary artery, right? The pressure here is about what? Like 25 over 10, right? Obviously millimeters of mercury. And when it gets to pulmonary capillary, what is it? The pressure here is about probably 7 millimeters of mercury, right? And this is probably going to be like around like same, like probably like 5 to 6. So we'll just say 6 millimeters of mercury for our case. Like, okay, sorry, it's a little lower than that. It's going to be probably like, okay, like 4 to 5 millimeters of mercury. That can go from like 2 to 10 to like, okay, different books says different things. But now, look, if you look at these things, right? Look, this is my pulmonary circulation. Like this part is my pulmonary circulation. This whole part from here, left heart to going to all these organs, that is going to be my systemic circulation, right? Now, what is the difference we have to understand? Look at the first thing we have to look at it. Look at the pressure. Look, usually what happens is that your left side of the heart have a higher pressure. Reason why is because your left side of the heart, these left ventricles are like thicker compared to the right ventricle. They're much more thicker, okay? Because they're much more thicker, and they should be much more thicker, the reason why is because they have to supply to all the systemic circulation. They have to supply to all brain, kidney, GI system, sclera, skin. They have to supply all those organs. Because of that, they have the higher pressure systems comparing to the thicker wall compared to your right ventricles, okay? Because of that, because of thicker wall, what happens is that they were able to generate higher pressure. Your left ventricle is able to generate higher pressure up to 120, but your right ventricle, if you look, it's only able to generate pressure of like 25, okay? So because of that, we said that because this one, your left ventricle is thicker wall system, which the right ventricle is a lot more thinner compared to it's a lot more thinner compared to your left ventricle, right? And if you look at the pressure difference right here, right? Whenever there's a pressure, because of that, your aortic pressure is also going to be different, right? Because it's going to be 120 over 80, right? That is the pressure that you see in the arterial side, and then you see in the pulmonary, on the aorta, and the pulmonary, or you see the 25 over 10, right? And now, one of the most important thing is that we have to look at what is the driving pressure for this one, and what is the driving pressure for the pulmonary circulations, okay? So for that one, we need to find the mean arterial pressures of each one, and we have to compare. So what is mean arterial pressure? Mean arterial pressure is equal to what? We need to know the we need to know the diastolic pressure, right? Plus, it's the 1/3 of a pulse pressure. What is the pulse pressure? Pulse pressure, basically, this is what my systolic pressure, and this is diastolic, right? This is a contraction pressure, this is a relaxation pressure. So you just do 120 minus 80, right? So 120 minus 80. Okay, if that's the case, then what do? The mean arterial pressure is equal to what? Your diastolic pressure is what? Your diastolic pressure is my 80 plus 1/3 of my 120 over 40, right? What is that going to give me? Mean arterial pressure is equal to what? 80 plus 130, like that's going to be 13.3. That's going to be like 93.3 probably millimeters of mercury. Okay? This is going to be my mean arterial pressure. Okay? Now, this is a mean arterial pressure for systemic circulation. Let's look at the mean arterial pressure, because remember, this mean arterial pressure tells me that the driving force that in the pressure, because remember, there has to be pressure gradients, and then what is the driving force? So this is a driving force 93.3 millimeter mercury to push all the blood to the systemic circulation. And if we look at this pressure right here, okay, what is this? At my mean arterial pressure, or let's say mean pulmonary pressure, because the mean arterial pressure for the pulmonary side is that, okay, what is my diastolic? 10 plus 1/3 of my pulse pressure, like 25 minus 10, that's 15, right? So in this case, mean arterial pressure is what? I have 10 plus 5, which is a 15 millimeters of mercury. Look at this. You see there's a huge difference? So that means we can say that in the pulmonary circulation, let's just write it down here. The pulmonary circulation right here, one of the difference of pulmonary circulations, or because this is driving the pulmonary, right? The pulmonary circulations is a low pressure system. And then we can say systemic circulations is this is systemic, it's a high pressure system, right? That's the number one thing we have to know, right? Because the pressure is that. But now we also have to know, okay, what we are throwing with this pressure? We are throwing the blood, right? The cardiac output. So remember, how much cardiac output is generated by this heart per minute? What is cardiac output is equal to? Remember, cardiac output is equal to amount of blood ejecting per ventricle, right? Which is this, each ventricle per minute, right? Which is a heart rate. So this is my cardiac output, stroke volume times heart rate. That tells me that how much amount of blood is ejecting per minute by each ventricle, right? So in that case, like this, usually normally it throws out how much blood? About 5 liters per minute, right? That's my cardiac output usually. What about this right side of the heart? All this blood is going systemic circulation, and everything, all the blood from like, look, this inferior, like superior vena cava, right? It's bringing blood from your head and neck area, right? And then all this from the lower part of your body is carrying from the inferior vena cava and draining into your right heart, right atrium, right? That means all those deoxygenated blood is actually draining into the right side of the heart. That means the cardiac this right ventricle is also pumping out those deoxygenated blood, right? That means it's also pumping out all those blood. That means it also pumping out those 5 liters per minute. The cardiac output for the right ventricle is also gonna be 5 liters per minute. That means, what does that tell me? That means my flow, right? Because cardiac output, I could even say that cardiac, like I could say this, my Q is equal to what? My Q is basically is equal to, I could say, okay, let's just say this, there is a whole equations of this, but my flow, right, the blood flow is equal to my cardiac output, right? So my flow is equal to like delta P over resistance. I could do that, but basically is that my flow for this, for my right side of the heart, or my cardiac output is exactly the same, right? So one of the similarities between the cardiac output and one of the similarities between pulmonary circulatory system and circulation is my flow. The flow is going to be the same, meaning that the cardiac output is the same. All right. That means they're both ejecting the same amount of the blood volume per minute. That's what it means. Now, but then if we talk about that, what about the velocity then? What about the velocity? We're talking about flow, right? Okay, the flow is the same, but what about the velocity of the flow? What is velocity? Velocity is equal to what? Velocity is equal to, okay, whenever we talk about the velocity, right? The velocity is equal to what is going to happen. For the velocity, you need to know the distance, right? So remember, let's forget about this. Let's just think about it. What is this? This pulmonary circulation is, what is this? It's sort of circulation combined to the system circulation, because system circulation is going to all parts of the body, right? So because of what happens is that velocity is going to be what? The velocity of velocity of flow, right, in my pulmonary circulation is going to be higher, right? Because it's shorter circulation, it's shorter. That means it's going to go much more faster. But what about my systemic circulation? What is my flow going to be here? Let's just write down the flow right here. Okay, we write the flow is the same, right? Flow is the same on the both sides. But my velocity is what? Velocity comparing to the pulmonary circulation, my velocity is low, right? The velocity of flow, the blood flow is going to be low because of longer circulations, correct? So velocity of flow is going to be shorter, right? Now, we talked about pressure. We talked about flow is going to be the same. We talked about the velocity is going to be higher, right? Now we have to talk about the resistance, okay? Because that's also very, very important, right? Now, what happens to the resistance? That's something that we have to understand. Okay, what is usually resistance? What is the resistance tells you? We have to talk about this resistance, right? And this resistance, whenever we talk about resistance on the pulmonary side, we call them a pulmonary vascular resistance, and this side we call them systemic vascular resistance, right? So pulmonary vascular resistance is what? Is basically equal. I can simply say 8NL. This is the equations that usually use, and the pi to the radius 4, right? That's the equation. And systemic vascular resistance equation is exactly the same too. Here, come back here, and we'll write down systemic vascular resistance is also equal to what? You can say 8NL, which is the N means viscosity, and this is length, and the pi to the radius 4, right? Now, if you look at this, what happens is like, that's a couple of things you have to understand now. Look, when the cardiac output comes in, right? Look, one thing is that this, the blood vessels on the systemic circulation, what happens? Those arterioles, what do they have? They have a lot of smooth muscle cells, right? So they have a lot of these vascular smooth muscle cells, okay? Because they have a lot of these vascular smooth muscle cells, usually they are tonically contracted, right? Because they're tonically contracted all the time, or we can even say the semi-contracted all the time, because they have a lot of the vascular smooth muscle cells. Because a lot of these vascular smooth muscle cells, what happens is that decreases the internal diameters of these blood vessels, right? So remember, if you are decreasing, because of decreasing internal diameter, okay, no, that's number one thing, internal diameter, okay. Other thing is that because they're tonically contracted, you're decreasing the internal diameter. Because a lot of these smooth muscle cells are there, what happens is that they're less compliant, okay, because they're less compliant. In this case, what is going to happen is that, okay, they are not thin wall, they also have a lot of these elastic properties there too. So because of that, what happens with that resistance is, remember, that means your SVR is equal to what? Your 8NL, and then your internal diameters, the radius are like you decrease, right? So whenever you reduce a decrease, what happens? You have a high systemic vascular resistance. So that means your systemic circulation is a higher resistance. That's what it says, right? But now we have to compare this. But this one, it's greater, right? But let's see where pulmonary circulation is a higher or low. Pulmonary vascular, what are the compositions of this in your smooth muscle cells? One of the things of smooth muscles, one of the things is that, okay, here what happens is that, look, these pulmonary arteries, they're shorter, right? They subdivide so much. They subdivide so much that they make up to like 280 billion capillaries. So in the pulmonary circulations, you get to say about 280 billion capillaries. You know how much that is? That's crazy amount. And for the how many alveoli are usually present there? About 300 million. Okay, there are 280 billion capillaries are present there, right? So think about this one. 280 basically means this to supply this 300 million capillaries. So about 300 million capillaries. That means those alveoli are literally showered, in this 280 billion capillaries. That means that much blood, like that much, this capillaries are there, and that makes it like huge surface area, right? When the 280 billions, when you add all of them, that's going to make a huge surface area, right? And if you have a huge surface area, what happens? And they have a huge surface area plus. They have what you call this, these capillaries are very thin wall. Okay, they are very thin wall. Okay, because the capillaries are because they divide into 280 billions, they are very thin wall. If they are more thin wall, what's going to happen? Okay, they are thin wall. Because of that, what happens is they are easily distensible. Okay, that means they are more compliant. Okay, and other thing is that because of thin wall, their internal diameters is also higher. So they have internal diameters. Okay. Internal diameters of the blood vessels is higher, plus because of thin wall, they can be easily compliant. Okay, it can be compliant or more distensible, if you want to say more distensible. So whenever more distensible, you can have, what do you get? You can easily extend out, right? So because of that, what happens is that their pulmonary vascular resistance are more compliant. The radius gets bigger, so internal diameter goes up. They're more compliant, goes up. The pulmonary vascular resistance goes down. So now. These are the couple of differences between that we just talked about. Okay, one other thing that I'm going to quickly talk about. Pulmonary, like systemic vascular resistance, okay, the systemic circulations is a higher pressure systems. Okay, your pulmonary circulation is a lower pressure system. Systemic circulation is a higher resistance system. Your pulmonary vascular resistance, lower resistance system. There is a velocity of flow is higher. Velocity of flow is lower in your systemic circulation, but velocity of flow is higher in this pulmonary circulation. But blood flow is going to be relatively the same. Blood flow is going to be the cardiac output is going to be exactly same to each one of them. So these are some of the differences that I had to talk about. And then other thing is that this systemic circulation is a thicker wall. This one is a thinner wall. Okay, the capillaries in the pulmonary capillaries are thin wall, right? These are thin wall. They have less. They have less smooth muscle cells. The arterioles in here, they provide more resistance because of the lots of vascular smooth muscle cells plus. With a lot of vascular muscle cells, and they're less compliant. Okay, so these are some of the differences between your pulmonary and your systemic circulations. Okay, now after that we also have to talk about some other things. So what do we talk about now? Before we go anything, now let's quickly talk about. Whenever we talk about this, the pressure, right? I would like to show a graph actually. Whenever we talk about the blood vessels, right? Usually, if you want to look at the graph for this one, okay, let's just make it down here with the blood pressure. We can make this blood pressure right here like this. Okay, let's make this blood pressure right here. With the graph, sometimes you can see graph like this. Okay. So what happens is that you can see this is pressure right here, okay? And I can make this as, okay, this is on my pulmonary side, right? And then here usually you can make as a 10. okay? And then sometimes you see a graph like this, okay? Usually you're working on this case, your systolic and diastolic, right? This, okay? Something like this, right? So when you see this graph, basically, because as you go to pulmonary capillary, what happens? The pressure goes down, right? This is 80 because this becomes like 7 or something. So if you see something like this graph, now this is like around like your capillary, which is there's a pulmonary capillary, you could say that. Okay, with the pressure is about like 7 or something. We'll make this, okay, let's just make this pulmonary capillaries here, which is like 7, something like that, right? So whenever you see this graph like this, basically this is a 25 right here, and there is a midpoint right here, okay? And this is going to be like about like 50 meters mercury. This is going to be your what? The mean pressure that actually drives this pulmonary circulations. That's how, like, you know, if you look at the, you can see, and people with the, like, you know, pulmonary hypertension, this graph would be probably, you know, the systolic, this would probably go up to like 40 or something. So this is how they usually show that in your graph, okay? Now, after this, we have to talk about pulmonary vascular resistance on when it comes about what is the differences between the the pulmonary vascular resistance versus long, and then what is the pulmonary vascular resistance with like different long volumes, or we also have to talk about the what is going to happen down here whenever there's exchange of gases happens. That's also we have to know, because we have to talk about the blood and gas interface. That's what we have to talk about too, right? So now, before we go, let's talk about blood and gas interface. What does that mean? Let's talk about blood and gas interface, okay? We'll write on blood and gas interface. All right. So now, what happens? The blood and gas interface basically means that, okay, this is the blood capillaries, right? What is happening here is that you're basically exhaling what? You're exhaling. Let's just write down. You're exhaling carbon dioxide from here, right? And then, okay, and then let's make a red blood cells right here. Okay, and then let's make this as you're bringing what? You're bringing oxygen in, correct? That's what you usually do. Look. In order to have a proper gas exchange, okay, we need to understand what is the capillary length, okay? And usually the capillary length, the diameter is about like, this is going to be like about like 0.75 millimeter. That's the length of the capillaries, okay? And whenever your red blood cells travels from this your this side, which is the pulmonary arterial side, to the end of this capillary, okay, and becomes the pulmonary vein, right? It is also about like 0.75 seconds, okay? This is the length of the capillary, okay? So 0.75 millimeters, and this is how much it takes travel from your red blood cells to get to at the end of the capillary length, okay? And in this time frame, what happens is there should be a gas exchange happens. Okay, even though it's a high flow system, because remember, it's the high velocity is higher even the high flow system, because of the length of the capillaries, because it's long, right? Because of this, it provides enough time for to have a good gas exchange. Okay, it provides the ample amount of time for having a good exchange of your exhaling carbon dioxide and bringing the oxygen in. And if you want to remember, like what is the size of this cap? It's about like 7 to 8 like microns. I think that's what it is, right? Now, if you know this, like, you know, by having the length of capillaries and then also the time that travels with 0.575 seconds, it's enough time. But this time, this transit, that's called transit time, it can be decreased too, right? Because what happens, like, based on the velocity of the blood flow, because remember, what happens, especially when you exercise, this transit time can decrease, okay? It could become a lot shorter because the velocity in the exercise would be a lot more faster. You see what I mean? But still, it's a good amount of time. But even though the most of the time I exercise, what happens is still though, when the blood leaves the capillary, it's still the positive pressure of oxygen is like 100 millimeters of mercury. Okay. Later it drops out. But just wanted to let you know that because of this capillary length, it has enough time to have a good gas exchange between between alveoli and your pulmonary capillaries, okay, because of length. Now after this, we have to talk about a couple of things. One of the things we have to talk about is the the pulmonary vascular resistance, okay, with the lung volumes and also the blood and that kind of stuff too. Now, if we want to talk about the pulmonary vascular resistance and systemic vascular resistance, the one more thing that I also have to mention right here is that, okay, let's just talk about like this pulmonary vascular resistance, right, is equal to, sorry, I think I made a mistake here. This is actually just, let's just say resistance here. This is resistance, and even here too, what is this? Down here, this is our resistance. Now, because when we find the pulmonary vascular resistance, there's one equation we have to do, because we have to look at the pulmonary vascular resistance as like whole, not as a one side, because before that I was just doing as a one side. We have to look at the whole side, okay? Because pulmonary vascular resistance and systemic vascular, they're different things. Because whenever we talk about pulmonary vascular, we have to look at the whole thing. What is the difference from here to all the way to your left atrium? So with the pulmonary vascular resistance, we need to find out, okay, what is the mean atrial pressure? And then we have to subtract by the left atrial pressure for the pulmonary vascular, because this one minus that one, and also I have to know the cardiac output, okay? That tells me about my pulmonary vascular resistance of that, okay? And if I need to find the systemic vascular resistance, I have to do, okay, what is my mean atrial pressure minus, because it's bringing blood back to all the way to right heart, right? So that's what we have to figure out. That would be my right atrial pressure, okay, over the cardiac output. That's how you find the pulmonary vascular resistance, systemic vascular resistance, because whenever we talk about the systemic, we have to talk about it as a whole, okay? Not as an individual. So in that case, like, let's just do this. What is my mean atrial pressure of my pulmonary vascular resistance? We said it was what? 15 millimeters of mercury, right here. So it's a 15 millimeters of mercury. And then we said, what is the left atrial pressure? Okay. Left atrial pressure is, we'll say this one is like here on our left atrium, we'll just pick as a 5, right? And then what is going to be my cardiac output? Cardiac output is about like 5 liters per minute, right? 5 liters per minute. Now, that will give me my pulmonary vascular resistance, okay, and we'll do the math. And systemic vascular resistance is what? What is my mean atrial pressure? Well, usually it's like 93, we'll just say 93 for now, because that's what we find out, right? And my right atrial pressure, what is this? We say 2 to 5, right? And for this one case, we'll just say, okay, we'll make an average of that. We'll say 3 millimeters of mercury, for it makes it easy, and we'll just 5 liters per minute. So when you do the math, right? So when you do 15 minus 5 is what? 15 minus 5 is gonna be my 10, right? So 10 divided by 5, that gives me my 2, right? 2 right here. And then you do 93 minus 3, which is 90 divided by 5. That's like 18. Okay? That's like about 18. So this is 18. Okay? Now if you find the ratio between this, let's find the ratio between the PVR over SVR, okay? And I could do the 5,000 ml too, right? And if I do that, you have a 2 over 18, right? And that's gonna give me what? 2 over 18 is like 1 over 9th, right? Look, this 1 over 9 tells you what? Pulmonary vascular resistance is about 1 over 9. The pulmonary vascular resistance is 1 over 9th, or sometimes you can get 1 over 10th too, depends. It's a 1 over 9th, okay? Pulmonary vascular resistance is 1 over 9th of your systemic vascular resistance. That's what it tells me, right? It's like that much, like lower comparing to the systemic vascular resistance. That's what pretty much, with the, mathematically, this is what you get to, here you get to see it, okay? Now, this is when it comes to blood vessel, right? Now we have to talk about we have to talk about the same with pulmonary vascular resistance with the change in lung volume. What is going to happen whenever your lung expands or whenever your lung decreases? What are the changes you get to see in the pulmonary circulation? That's what we're talking about right now. Before we talk about the pulmonary vascular resistance with the lung volume, there are a couple of things we have to understand is that